Hello, we're continuing with the second video of chapter 19. In the previous video, we became familiar with the open loop control mode and its limitations. Now, let's look at how a closed loop control is different.
Take the example of making popcorn. With the open loop control, we have no feedback on whether we have actually achieved the desired outcome. For example, if you calculate that it takes 3 minutes and 45 seconds to make popcorn in your microwave, you leave it unattended after starting it. After exactly 3 minutes and 45 seconds, the microwave finishes and the popcorn should be ready. However, not all popcorn bags are the same, which can lead to some kernels remaining unpopped, while others become burnt. To achieve perfect popcorn, it's important to monitor the popping process closely. When the frequency of pops slows to about 2-3 second interval between pops, it's time to turn off the microwave. This ensures that the popcorn is ready without any burnt kernels. This is already a closed loop control because we constantly check the state of the corn preparation and intervene in the operation of the microwave on this basis. The time it takes to cook depends on the current bag. It is not a fixed time. It could be that it was ready after 3 minutes 32 seconds, or it could be that it was ready after 4 minutes. The main difference is that we don't prepare the popcorn in a pre-calculated way, but check exactly when it is ready.
So, we talk about closed loop control when there is feedback in the system. This means that the output, controlled value, is also measured, and this value affects the actuating signal. The common property of the controllers is that they form an error signal from the setpoint and the feedback. The setpoint is marked by RA, the feedback by YE, and the error signal by E. The controller's task is to make this error signal 0, because then the controlled signal must be equal to the setpoint. A p-type controller multiplies this error signal by a constant kp value, so the actuating signal, denoted by U, is proportional to the error signal. The name of the controller reflects this, as the letter P is derived from the word proportional. This means that the greater the error, meaning the more the output signal deviates from the setpoint, the greater the control action will be. However, there is a crucially important corollary. If the error is 0, so our system has reached the desired state, then the actuating signal is also 0. In ideal or lossless systems, this would not be a problem, but in reality, everything has a loss. The motor windings have resistance, the motor and gearbox bearings create friction and break the motor. Because of this, you need some kind of actuating signal to keep the motor turning. However, if the actuating signal is not 0, the error cannot be 0 either, since the two values are directly proportional. This means that in theory, it is not possible to achieve the setpoint exactly with the P controller. In technical jargon, we say that the P controller always sets with a residual error.
Our model will be the same as the one we drew during the open loop control, as the motor and the gearbox have not been changed. The feedback will be provided by a sensor, which in this case will be the encoder on the motor shaft. It is important to note that this sensor does not necessarily measure the control signal directly, but in some indirect form, so we need to modify the sensor signal accordingly. In this example, the control signal is the shaft of the gearbox, and the encoder measures the speed of the motor shaft, so we need to account for the gear ratio.
Our controller will be the previously discussed p-type, which multiplies the error signal, which is the difference between the setpoint and the feedback signal, by a constant to produce the actuating signal. This will be a PWM signal, which will be connected to the motor via the motor driver. Our controller loop is therefore made up of several elements. A controller, which includes the P controller and PWM signal in the microcontroller software, and the motor driver, which amplifies this PWM signal according to its supply voltage. Our process, whose model is unchanged, consists of the DC motor and the gearbox. The unknown load is also present on the gearbox shaft, as well as the sensor mentioned earlier, which in this case is the encoder. The speed of the motor is fed back to the controller through this sensor.
One might reasonably ask if the encoder was also connected in the case of the open loop control, and the measured speed was also displayed, so what is the difference?
The difference is that we did not use the value of the encoder anywhere in the calculations of the control, We just wrote it out for ourselves to see how the control worked. Feel free to try it. Disconnect the 4 wires of the encoder and test the previous control program. It works exactly the same as before, but you can't see the actual speed of the motor and gearbox. In control, the speed measured by the feedback signal, in this case the encoder, is essential to accurately determine the value of the actuating signal and the modified characteristic. If the encoder were to be disconnected here, the motor would not operate anywhere near as the reference signal dictates.
Load the project Lecture 19 P controller into the software development environment and upload your program to the development board. In the file controller.c, you will find the function runProportionalController itself, which implements the control. Let's see how it works.
The ref speed RPM value is passed to the function. This is our set point. The output speed RPM variable is the speed of the shaft calculated from the encoder signal, which is our feedback signal. The difference between these two is the error signal. The controller output is the actuating signal, which is obtained by multiplying the error signal by the controller parameter kprop. The actuating signal is then output as a PWM signal to the motor. Use the button on the right to set the set point from 0 to 160 RPM and record the actual RPM. An opposite rotation rate would give very similar results.
You will notice that there is a significant difference between the set point and the actual speed. We also experienced a similar problem with the open loop control, where calibrating the motor parameters solved this problem. So let's do the same here and see what changes. In the motor.h, change the original values to the values measured at the control. Of course, everyone writes their own measured values here.
If you repeat the measurement with the corrected parameters, you get an interesting result. We can see that the situation has not improved compared to the previous measurement. This is because the p-type control does not use the model parameters at all. While in the case of open loop control, the actuating signal is generated based on the model properties. In the case of p-type control, the error signal determines the actuating signal. Earlier, we discussed that the P controller always sets with a residual error. And the value of the residual, the steady state error, depends on the value of Kp. The higher the Kp, the smaller the residual error will be, as can be easily seen by looking at the equation of the regulator. However, a higher Kp value will lead to instability of the controller. Imagine that you're balancing on a rope. To keep your balance, you need small subtle movements, low Kp. If we start to sway with high momentum, high Kp, we start to sway more and more on the rope, and in the worst case, we could fall off. The P part in the controller has the same effect.
The main.c file contains the setting for the Kp value.
Change its value from 4 to 20, upload the code, and set an arbitrary set point using the left and right buttons. We can see that the motor is spinning back and forth, unable to adjust to the given value because it is too forceful, always falling over the other side. If we reduce the Kp value from 4 to 2, we will have too much residual error.
Let's give it a try. Take the originally set value of Kp equal to 4 with a set point of 40. The shaft rotates at about 28 RPM, which means 12 RPM is the residual error. Change the Kp value to 2. Now let's see what happens when we set the set point to 40. So now the shaft is only rotating at about 20 RPM, which means that the residual error has increased to 20 RPM.
The question may arise, how can we find the right value of Kp? We have 3 options. The first is the heuristic tuning, where we try to do it by intuition or randomly. The second option is the model-based tuning, where we use the system to calculate exactly the right settings. And the third one is the rule-based tuning using empirical formulas and rules of thumb.
The first method has not been proven in control engineering. However, if you have many years of experience setting up this type of system, you can quickly achieve an acceptable result. Without practice, it is not really worth trying this method. Model-based tuning would require more mathematical and control engineering skills, which you will encounter in higher education.
We will now present the third option. There are many methods that promise to tune your controller by making simple measurements and then using empirical formulae and rules of thumb. Examples include the Cohen-Kuhn, Kappa-Tau, and Lambda methods, but the best known is the Ziegler-Nichols method, which we will now discuss in more detail.
An empirical formula is a relationship that has no mathematical, physical, or other scientific theory or law behind it, but after much experimentation and analysis of the data, it has been found to work quite well in practice. Rules of thumb provide easy-to-use, good approximate estimates for complex, intractable problems. You will come across many of these empirical formulae and practical rules in engineering.
You've heard about this method in the previous chapter, so we'll just briefly summarize the rules here. First, set your controller to p-type only. This doesn't make much difference here, since we're using a p-regulator by default. Set Kp to a low value, where the system is stable, then increase Kp until the system starts to oscillate. After that, record this critical Kp value and measure the period of oscillation. Based on these, use the following table to set the parameters for the P, PI, and PID controllers.
Upload the example program Lecture 19P controller at Ziegler-Nichols to the development board. Here we switch a square wave signal to the motor. For 1 second the set point is 0, then for 3 seconds 50 RPM. We can adjust the Kp value with the up and down buttons. Increase it until we see a continuous oscillation on the display.
Bence, please run the code and increase the Kp value. You can see that the RPM starts to oscillate. Its value waves back and forth. In other words, it oscillates. We're looking for the point at which this oscillation becomes constant, neither decreasing nor increasing. Here, we can still see that the oscillation is weakening, so we still need to increase the value of Kp. Now that we have found this point, the speed oscillation has stabilized, which is the phenomenon we had to achieve. If we increase the Kp further, we can see that the amplitude of the oscillation starts to rise, so we've gone beyond the state we are looking for. Let's return the Kp to the value where we experience the constant oscillation. In our case, it was about 8.1. There is no need to be extremely precise about this value, as the empirical formula we will use to calculate it will only give an approximate result anyway, not the best possible one. Now, we just need to read the period time of the oscillation from the display. The easiest way to do this is to take a picture of the display and count the pixels. On the diagram, 1 pixel in the horizontal direction represents 20 milliseconds, and the period is calculated to be 14 pixels wide, or, as I calculated, about 280 milliseconds. Of course, you may get slightly different results, so everyone should make further adjustments according to their own results. Based on these, the t-critical value is 0.28 seconds. For the tuning of the P controller, the formula in row P of the Ziegler-Nichols table should be used, where the tuned Kp is obtained by multiplying the value of the critical Kp by 0.45. This gives a Kp of 3.645.
Set the calculated Kp value in the main.c file and reload the code. What do we observe?
The motor will maintain a stable speed at the 50 RPM set point with a residual error of 18 to 20 RPM.
And what happens under load?
Let's go back to the project of Lecture 19 P controller and set the Kp parameter of the controller to 3.645. The left video shows the unloaded condition and the right video the loaded one. We can see that if we load the motor, the error signal increases and the actuating signal increases with the error signal. The implication is that although we did not measure the load itself, the controller sensed that something was blocking the shaft and sent a larger signal to the motor to compensate. Again, it is important to note that the residual error of the P controller increases in proportion to the load.
As we are coming to the end of this video, let's summarize our experience with the closed-loop P controller.
We've seen that we do not need to know the model or the parameters of the motor perfectly in order to get the system to work well. Essentially, we did not use any of the motor parameters, only and exclusively the gear ratio of the gearbox, and only because our encoder is not on the output shaft, but on the motor. We didn't have to use the equation of the motor either. The only calculation we had to perform was a multiplication operation to tune the controller. However, we do need a sensor to measure the controlled signal, in this case the speed of the motor shaft. On load, the controller behaves better than the open loop controller, but it has the huge disadvantage that the system never reaches the required value. There's always a residual error.
It would be good if we could somehow eliminate the residual error. Don't worry, that's what we'll look at in the following video, so stay tuned.
Bye.